And our next speaker is Dr. Jing, and he will talk about intratympanic delivery of nanoparticles. Okay, can we have the presentation?
Yeah. Good morning, everyone. Thank you, organizer and the chairman, for giving me a chance to present our work here. I will talk on inner ear therapy using intratympanic delivery of nanomaterials. I will focus on 3 issues: targeting, pathway, and safety. Why should we use nanomaterials for this inner ear therapy? Because we want to improve the efficacy of therapeutics using protection, enhancing penetration, and providing targeting. We can achieve the targeting either use anatomical targeting or molecular targeting. Actually, the intratympanic delivery is broadly used in the clinic because it's high in efficacy, low for the delivery dosage, and it's safe. Actually, this intratympanic delivery is already a targeted delivery because it provides a shortcut to the inner ear by avoiding the long trip of the intravenous injection. So the inner ear is composed of vestibular and cornea, 2 parts. It's well accepted that this round window is responsible for the drug entering the inner ear. But recently we found the oval window is more efficient than round window to bring the drug to the inner ear. It can bring both to the vestibular and the cornea, to this compartment, instead of directly to the tympani, this compartment. We further improve the targetability of this intratympanic delivery by using the targeted tympanic medial wall delivery. We use a special catheter to inject the materials on the surface of the medial wall. The material, they were diffused towards the oval window and the round window. We only use very little volume. For example, in the animal, we only injected 2.5 microliters. We use the gadolinium daughter as a tracer because it's visible in MRI. We can easily do this in vivo study. After 30 minutes, we can see the abundant uptake in the vestibular and in the corneal, tympani, vestibular, not in the endonymph of this media. Also, we developed a targeted vestibular delivery by using this oval window pathway. We injected the substance to the atic compartment here. Then it will diffuse along the auricular chain to the oval window, and then to the vestibular. In order to prove this oval window pathway, we seal the oval window, and then we try to prevent the specific uptake in the vestibular. We still use gadolinium daughter. In the normal inner ear, you see the uptake in the vestibular and in the cornea. So this is through the oval window, here is through the round window. So if we inject the gadolinium to the atic compartment, so they distributed specifically to the vestibular and the vestibular, but not to this tympani. So if we seal the oval window, we can only see the uptake in the tympani, not in the vestibular. But after even 35 minutes, we found a little bit of distribution in the vestibular because the gadolinium diffused from the cornea to the vestibular. We tested plenty of nanoparticles. Actually, most of them didn't work for the in vivo study because the signal was very low. We succeeded with 3 types of nanoparticles. Actually, these 2 are spion, and this nibosome. They worked for the in vivo study. Only this CLINAM spion and the nibosome, they passed the 2 windows efficiently. But the others, we don't know yet because they are not workable with MRI. So this figure shows the uptake of the CLINAM spion. So this is the structure of this particle. In the inner ear, after tympanic medial wall delivery, we use a T2-weighted MRI because in the normal cornea, the fluids, they generate the bright signal. When this spion distributed there, they clear the signal, so this area becomes dark. So we deliver to the left ear. You say after 3 hours, they distributed. After 6 hours, there's some signal recovery in the sclera tympani and the sclera media, but not in the sclera vestibuli. After 2 weeks, they're full recovery. So here shows how to this spion modify the signals. In the normal situation, you can see all these areas bright with distribution, the clear signal according to the distribution of the spion. So this figure shows the distribution of a nibosome in the inner ear after the middle ear delivery. We still use gadolinium delta as a tracer. They were noted in the nibosome. After 3 hours, you see the distribution in the vestibular and in the cornea. This signal is from the middle ear, so it's much stronger than in the inner ear. After 6 hours, the distribution increased in the vestibular and the cornea, but reduced in the middle ear. So by analyzing the ratio of the signal intensity of middle ear to the inner ear, we can get how much the spion passed the windows into the inner ear. So it's a size-dependent distribution. The smaller the size of nibosome, the more efficient they enter the inner ear. We also performed the histology study because the other particles, they were not workable with MRI. So we used fluorescence to analyze the distribution in the inner ear. Actually, these 3 particles, the lipid core nanocapsule, PEG, PCL, polymer serum, and the hyperbranched polynesium, they also entered inner ear efficiently. But this spion, the POA, is only acid polyronic copolymers coated spion. They didn't pass efficiently, so because of the coating. Actually, this particle is, so it's a complicated name. It's an spion is generated using this ferric ammonic nitrate mediated oxidation of this Fe3O4. So a little bit different from this spion. This figure shows the distribution of the polymers in the inner ear of the intratympanic delivery. So we can see the distribution of these polymers, the red signal in the round window membrane in the cornea. Also in the vestibular, there are abundant distribution in the utricle and the sacral. We use the corneostomy as a positive control. Definitely you see more distribution in the round window and the inner ear. Also in the vestibular, they are similar. Because we deliver to the cornea, tympani, the distribution in the vestibular is a diffusion from the cornea to the vestibular. So it's less than in the cornea. This figure shows the distribution of hyperbranched polynesium in the inner ear after round window membrane delivery. You can see the distribution of these particles, the green signals in the round window, in the middle ear, the neuron, spike ganglion, and the cortical organ, outer hair cells, inner hair cells, and the cerebrovascular rays, spinal ligament, and also the stability artery. But they also enter the nucleus efficiently, which means they're good for gene delivery. But I will not present the gene delivery here now. And now come to the targeting. We selected 3 targets for the study. One is presentin on the outer hair cell, another one is the track B on the spinal ganglion cell, and another one is GM1 on the nerve fibers of spinal ganglion cells. We use presentin peptide, binding peptide functionalized polymer cell for this presentin. Track B ligand functionalized ribosome for track B targeting. The Theta1 peptide functionalized polymer cell for GM1 targeting. We just proved the concept for this study. So where do they locate? Presentin locates on the surface of outer hair cells. The track B on the surface of spinal ganglion cell, and the GM1 on the nerve fibers of the spinal ganglion cells. This figure shows the outer hair cell targeting using the presentin binding peptide functionalized polymer cell. You can see the specific distribution surrounding the outer hair cells. But also you can see some distribution in other areas. But here is the most abundant distribution. Then there's no specific distribution with the control polymer cells. This figure shows targeting the nerve fibers of the spinal ganglion cells using the polymer cell. The green signal is the staining of the neurofilament of the nerve fibers. The red signal is a polymer cell. This is a specific polymer cell. This is a scramble polymer cell. This is neat polymer cell without any peptide. If we do this co-localization, you can see only this specific polymer cell, they have the co-localization with neurofilament. So here shows the overview of the distribution of the polymer cells. So this red dot indicates a specific polymer cell. So there are abundant distribution along the nerve fibers in this canal. So how about the safety of the nanoparticles? We studied the safety of lipid core nanocapsule and the ribosome nanocarriers. They are safe for the inner ear. They didn't cause auditory function, morphological, or neural elements changes. For this ribosome, we analyzed the hyaluronic acid and the receptors. Why did we change the parameters? Because in our recent study, we found that the silver nanoparticle, they cause a hearing loss and upregulated hyaluronic acid in the inner ear. Also, the other cytokines, but I will not present here because it's different topic. So this lipid core nanocapsule, they didn't cause hearing loss. It's the APR thresholds. There's no difference between the treated and the control group. And they didn't change the distribution of this synaptophysin and the ribbon synapse. So here is the synaptophysin locates on the afferent, and the ribbon synapse locates here on the afferent. So after 2 hours and 24 days, there's no change on this synaptophysin and the ribbon synapse. The ribosome also, they didn't cause hearing loss, and they didn't change the hyaluronic acid and the toll-like receptor 2 and the CD44. You may see it has change here in the spinal ligament, but this, because this ribosome contains gadolinium, but the empty ribosome did not cause any change. So we consider maybe it's gadolinium caused this little change. I would like to acknowledge our partners. We have 9 partners involved in this study from Israel, Finland, Sweden, France, Germany, UK, and Switzerland. The study was supported by EU FP6 nano-year and FP7 nano-CI and the National Nature Science Foundation of China. Thank you for your attention.
Well, since we used up all our time anyway, I thank the speakers for presentations. Thank you for coming, and we will end this session.
Thank you.